Welcome back to session 5. So today we are going to be uh, transitioning from the ancient world to the beginning of the modern world into territory that's going to look a little more familiar. So this is the overview of what we want to do today. Some of this background we already have covered. Uh, in the last few sessions, we have looked at flat Earth cosmology, the simplest model of the universe that you could come up with, and the Earth's place in that universe. Then we transitioned to a spherical Earth cosmology, a very common sense supported cosmology grounded in a very common sense physics by the Greek philosopher Aristotle. So we looked at Aristotle's physics. And then I think in the last session, we looked at extensions to the simple model that we had in our discussion of Aristotle's physics. And that was Ptolemy's geocentric model, which added a lot more details to the simplistic model we had here. And so Ptolemy's astronomy and Aristotle's physics, these two together were the accepted physics for uh, almost 2000 years in the Western world, at least. And challenging them was equivalent to challenging, or became at some point equivalent to challenging the authority of the church. And so today's focus is going to be on Galileo. I'll spend a little bit of time on Copernicus, but most of it would be on Galileo. And we will look at what Galileo discovered specifically in the context of astronomy, and we'll also look at how he got into trouble with the church and some of the uh, scientific work that was controversial at that time. All right, so quick recap. Aristotle, who was uh, with Plato known as the philosopher, like many of the philosophers in medieval times would not even take his name. They would say the philosopher has said this or that, and everyone would understand that they are referring to Aristotle. Aristotle's physics essentially divides all uh, objects in the universe as essentially made up of 5 elements, right? So 4 of them are found in the terrestrial world around us: earth, water, air, and fire. The earth and water being the heavy elements whose natural tendency is to move towards the center of the universe, which is also the center of the earth, and air and fire whose natural tendency is to rise away from the center of the universe, or away from the uh, center of the earth. And we saw how, based on this physics, Aristotle argued that the earth must be at the center of the universe because that's where the heavy elements would congregate. It must be spherical because that spherical arrangement would satisfy the maximum number of earth and water particles. And it must be stationary because once these particles are at the center of the universe, there's no reason to move away from that center. And so that's how the spherical earth at the center of the universe was explained and justified. For the objects you see in the night sky, because they are made up of, well, because they are seen to go in follow circular motion, which is not something we see naturally on Earth, at least not in any prolonged form. You can try to spin a ball or something like that, but that spinning won't last for long. So you might remember that there can be violent motion, unnatural motion that is initiated by a living being, but that unnatural motion won't last for long. Uh, Lasting circular motion is only seen in the night sky, and so that's because the entities there are made up of a fifth element called ether, and that's what makes up the sun, moon, planets, and stars. So that was the essential cosmology of Aristotle. And the rest, of course, there are a lot of details, but at a high level, that's what his cosmology was. And then last time we saw how Ptolemy, who was an astronomer based in Alexandria in Egypt, made numerous observations and made a very refined model of the cosmos, which was grounded in Aristotle's physics, but also added a lot more details. And uh, his work, for which he became famous, is known today as the Almagest. And we saw how complicated his model was. I showed you an animation last time, but even though it was complicated, it was very precise in its predictions compared to any other model or any other theory, which is why his model was the authority for the Western world till the time of Copernicus and Galileo, right? But we also saw that there were a number of uh, messy features that he had to add, such as moving the Earth slightly away from the center of the universe, or adding epicycles, the planets, for example, not moving in clean circles, but rather moving in little circles whose centers moved in a clean circle. Or sometimes you had double epicycles, right? Um, so we saw that last time. They were not very satisfying, like aesthetically satisfying, but they fit the observations really well. And so, and you might also remember how the linear speed of the orbit was also not something that Ptolemy preserved. He said that, well, the angular speed around a point, which is again off center, and in fact not even coinciding with the Earth. So he had to add all those complications to fit the observations. Anyway, so it was in the Renaissance that people finally started thinking seriously in a fresh direction. So the word Renaissance, which means rebirth, was like a phase where in the Western world, people started thinking that perhaps, we can come up with new things, right? Throughout, for more than 1,000 years, people used to think that the ancients were perfect. Whatever there was to discover or whatever there was to know, people in ancient times had already done it. And there were these massive monuments that, were testimony to the achievements of the ancients, which, you know, in the medieval times, they couldn't really match. And so there was a lot of reverence towards the ancients, specifically Aristotle as a philosopher. So when the Bible was written, the Christian Bible, it was not, there was no scholarly philosophy in the Bible itself. So as philosophers who were Christians tried to justify their belief in the Bible and in the theology of Christianity, they looked to Aristotle as the model, right? The model philosopher. And so they borrowed a lot of his philosophy and blended it with Christianity. And they blended it so well that even though Aristotle was not a Christian, he was living 300 years before the birth of Christianity, challenging Aristotle or challenging Ptolemy's astronomy became treated as if you're challenging Christianity itself. Uh, and so that's the environment in which Copernicus and Galileo uh, emerged. At the same time, during this Renaissance, like I said, um, uh, some people like Copernicus, Galileo, and others, they started looking beyond Aristotle. Okay, so they were dissatisfied with Aristotle's physics, dissatisfied with Ptolemy's astronomy, and they looked to other philosophers from ancient times uh, whose ideas might, you know, um, inspire them in a different direction. And so Plato and Pythagoras, for example, were two philosophers who Copernicus and Galileo looked towards. Their philosophies were different from Aristotle. They were much more mathematical in their outlook. Aristotle was not very math oriented. And Plato, in fact, had given this problem to the astronomers that you need to explain the motion of everything in the night sky using circles, right? Perfect circles which signify eternity, no beginning, no end to the shape of a circle. And so that was the task, which is why everyone was thinking in terms of circular motion. Even Ptolemy was thinking purely in terms of circular motion, and when the data did not fit circular motion, he added, he and others added epicycles, double epicycles, and so on to make sure not to deviate from circular motion. So Copernicus was actually a Polish guy. Uh, he was born in 1473. He actually became an orphan quite early in his life, but his uncle, who held a position of authority in a church there, he gave him the post of an administrator in a local church, which gave him sort of a stipend for life. So the word nepotism, for example, right? We talk about how certain celebrities benefit from nepotism. The word nepotism comes from the Latin word nepos, which refers to the nephew, right? Uncles favoring nephews and giving them positions in churches was very common and acceptable in that time. And so so Copernicus benefited from nepotism as far as his uh, living was concerned. But he was educated initially in Poland. He traveled also south to Italy to actually study medicine and law, right? The kind of law that would help him as an administrator of the local church back in Poland. So, but while studying medicine, he met a professor of astronomy at the University of Bologna in Italy, who really influenced him. And so this is something that can happen, right? Your major area of study can be medicine, but you meet someone who you meet a professor who might not be in the same field, but nonetheless can inspire you in a way that the influence can be very long lasting. So Copernicus got trained as a physician. In fact, he took care of his uncle in his old age, but um, today we don't know him for his what was his main profession that time, which was as an administrator in the local church, but for his famous work, uh, which when translated into English has the title On the Revolutions of the Heavenly Spheres. So influenced by this astronomy professor, when Copernicus looked back at Ptolemy's model, he felt that um, God, who is supposedly the most perfect of all beings, would it was very uncharacteristic of an omnipotent being like God to create a universe in which things were moving in such a messy and chaotic way, as Ptolemy's model seemed to um indicate. So there was this inherent dissatisfaction with the inelegance of Ptolemy's model. He felt that God's system needs to be more elegant, uh, right, to befit his good name. And being a mathematician, he felt that he could come up with a better model. And he had heard actually in ancient times of some people, like I said, people like him were looking beyond Aristotle. They would try to hunt for ideas from the ancient world which were coming from other philosophers. And he happened to hear that, in Roman times, there was someone who had proposed that the sun could be at the center of the universe. And so this idea did not originate with Copernicus. Um, but when Copernicus grappled with that idea, he came up with a model. He came up with a model of the universe with the sun as the center, and that's what heliocentric means. Heliocentric means Helios or sun at the center. Okay. Um, and if you assume that model, so that means the sun ceases to be a planet. If the sun is stationary at the center of the universe, it ceases to be a planet. Uh, he had the earth moving around the sun. So that's called a geokinetic model, the earth moving. And it had two kinds of motions. To explain the 24-hour daily, rotation of the stars and the sun and, the planets rising and setting, he had the earth rotate around an axis, which went through the pole, along which the pole star roughly was. So that's the diurnal motion or the daily motion. And then to explain the relative motion of the sun in the backdrop of the starry sphere, the sun and the planets that wander in the backdrop of that starry sphere, he had the earth itself wander once a year around the sun. Um, and as the earth goes around the sun, if you're looking at the sun, naturally the stars that are going to lie behind the sun are going to be different as you travel around the sun. And so that annual motion, yearly motion around the sun, was used by him to explain why and how the sun and the other planets wander. He had the moon go around the earth, though. The moon did not go around the sun, it went around the earth. So, in a sense, the moon ceases to be a planet, the sun ceases to be a planet, the earth itself becomes a planet uh, since it starts moving in that model. So, obviously, he was looking at a lot of data and he was fitting a lot of data to a mathematical, or you can say a geometric model of um, of the universe. Okay, that time for them, remember the solar system was the entire universe. There was no notion of other galaxies or and so on. It was the solar system, and on the outside you had uh, the celestial sphere of stars. So Copernicus argued that this heliocentric model, which is not a new model, but an old idea, but he sort of supported it uh, using a lot of actual data. One of the um astronomers in the ancient world who had proposed a heliocentric model was Aristarchus of Samos. And there were a few others that Copernicus had heard about. Now, what was his main argument for why this heliocentric model is a better model? His primary argument was simplicity. If you put the sun at the center of the universe, then um, the mess that you have, the complicated mess that you have in Ptolemy's system with, so many epicycles and all kinds of uh, tweaks and hacks that you have to add to that high-level geocentric model to make to fit the predictions, they all go away and you get something that is far more simple, far more elegant, and thus more likely to have been set up by, a god who is omniscient, omnipotent, and, having all these great qualities. He actually gives the example of how Ptolemy's model feels like, you grab a pair of eyes from one animal, the ears from some other animal, legs and hands, and you just like sort of stick them together in some random way. The resulting creature is going to look like a monster rather than something beautiful, right? So he didn't think that uh, this universe would be like that, and so he wanted to come up with something elegant, something beautiful. So the argument went something like this, that if the heliocentric model is assumed, like the model that he was giving, then you could explain the observed phenomena much more simply, right? You could explain the same things that Ptolemy could explain, but your model is simpler, it's more elegant. So simplicity, elegance was really the key to his conviction and faith in the truth of the heliocentric model. But the thing is, just because there are two different models that explain the same observations, um, we cannot say that one model is better than the other. Elegance is, of course, an argument, but it's not always the case that something that is elegant is more likely to be true. But Copernicus had that conviction. But I just want to mention this that it's not a logical uh, deduction to say that if you assume the truth of my model, then you get all these consistent explanations of all the observations. Uh, and because you see all those observations, therefore my model must be true. Right? Another way to say this is I can come up with a model that implies all the observations, the observed data, but this doesn't mean that the observations imply the truth of my model. It's just because A implies B doesn't necessarily mean that B implies A. Right? So there were two competing models. Ptolemy's model was also able to explain all the observations, although in a more messy way. And here is something inconvenient, which I kind of lied to you about. Copernicus actually could not get rid of epicycles. Right? When he tried to exactly fit the data, he had there was no way around but to add epicycles. He also could not get away from making the making the sun slightly off center from the center of the universe. He had to do that, otherwise, his model would not fit the observations exactly. So I'll just make that note that on the whole, Copernicus's model was simpler, uh, but Copernicus's model has epicycles. Okay, it has epicycles, although fewer, fewer than Ptolemy's model, and the sun is slightly off center, off from the center of the universe. So in a sense, you can argue that, well, some characteristics of a monstrous model are still there in this kind of picture. And of course, you know, the, uh, part of the reason why he had to have these features is that he was still stuck to it was still stuck to circular motion, still stuck to circular motion, circular motion and combinations of circular motion to explain everything, just like Plato had wanted. Now, there were other things that the model could explain more simply, and I'm going to show you one such thing. Remember, I told you last time about the retrograde motion of Mars, how, when you look at stars in the night sky and you track, say, a planet like Mars, it might appear to wander in one direction relative to the stars when you track it night over night for many weeks and months, but it might, drift back for a few days. That's called retrograde motion before continuing forward. So it was to explain this kind of motion that in Ptolemy's model we had epicycles, as you might remember from the last session. But here is how Copernicus's model explained the retrograde motion of Mars. He couldn't get rid completely of epicycles, but he could manage without many of the epicycles. And I'm going to actually show you um, an animation from the game that I had built. Uh, Kapil, let me know if I'm just sharing my desktop screen. Let me know if you can see that. Uh, yeah, can you see my desktop screen? Hello? Okay, you can see. Okay, cool. Uh, so I'm just going to play this animation. This is actually from my own game, but this is from somebody's channel. Somebody did a whole walkthrough. Uh, so I just found it on YouTube. So I'm going to play this. So what I did is I have a retrograde model, sorry, a heliocentric model inside the game, set up by this 13-year-old girl who just uses a lamp for the sun. And then there are these two circular tracks. Okay, there are lots of such models in the game, but I'm just going to show you one of them. Here we have the Earth. I hope you can see my cursor also. We have the Earth and you have Mars, right? And there is a laser light that is pointing from Earth to Mars. It's actually passing through. There's a hole in the ball representing or this layer representing Mars. It passes through Mars and it hits this outer periphery. And along the outer periphery, we have constellations. It turns out that not just behind the sun, but even behind the planets, you still have the familiar 12 zodiac constellations. Okay, so the moon, the sun, the planets, they're not found in completely different parts of the sky. They're still found to be wandering across the zodiac constellations. So I have the zodiac constellations uh, etched or drawn in this periphery. Okay, so what you're going to see here is as the Earth moves around the sun, notice how the red laser light, which is pointing to Mars, will generally tend to move in one direction, but temporarily, specifically when the Earth is overtaking Mars, you'll see the light moving backward for some time before continuing to move forward. So here it goes. So Mars is seen to move in one direction, but now as the Earth approaches it and it overtakes it, you see now it went backward for temporarily. But most of the time, you see that light moving forward. So Mars is seen to move uh, generally in one direction relative to the background stars, but where you see this paused is one stretch where as the Earth is overtaking Mars, you see it go backward um, relative to the stars, and you can actually click and place yourself on the Earth and see this happening from the vantage point of the Earth. So while sitting on the Earth, you can see that Mars is drifting to the right, in front of the zodiac constellations. So the general motion is it's drifting towards the right. Um, but what you'll see is as the Earth comes closer and is overtaking Mars, it will appear to change its direction and move backward. So this is a little hard to visualize without this kind of 3D model, which is the main reason I built this model to add to the game. So you can see here now it's moving backward. Okay, I think that's all that I wanted to show. So let me go back to my blackboard.
Oh, this is pretty cool. This
Yeah,
is very,
so you remember how I said that just the journal is not sufficient.
yeah.
Uh, you need
So, Omkar,
you need-
what we have to do is we have to figure out a way to make that game much easier to access. So I will
Hmm.
coordinate with you separately.
Hmm.
And we have a reasonably big tech team here. Whatever needs to be done, we'll do it so that we are able to make it available to people. It's a tragedy that it currently lies on such a heavy software.
Right, right, right.
So we'll
Sure,
fix.
sure.
Yeah.
Yeah, we can talk about that offline. So, you saw, right, from the animation that the retrograde motion of Mars is explained more simply, without needing epicycles, without needing epicycles uh, for Mars, right? So this is just an example of what it means um, for the model to be simple. You can see my blackboard, right? Just confirming that. You can see what I just wrote, this sentence. Okay, good. All right, so let me see if there are any questions. All right, some discussion on what the word philosophy means, but all right, somebody had a question. I just unmuted you.
Yes, so am I audible?
Yeah,
So for a fraction of time, it seems like Mars is not moving at all in the animation that you showed. Like when Earth was relatively near to it.
yeah, yeah.
Why
It's
is
it's
that?
it slows down and then it starts moving backwards.
So
Even
it's
in
still
relative
moving, but
motion, when you think about the velocity, the relative velocity, in order to go from right to left or positive to negative, it will have to pass through zero. So when it passes through zero, it appears as if it's not moving for some time. That's just because, it's turning around there.
oh, okay. But like in reality, it's still moving. It's just that we
Yeah,
cannot
in
see.
reality, it still moves. Also, whoever made that walkthrough, I think that person slowed down the animation. Actually, you can, inside the game, you can speed it up. So then you won't
Oh,
see it pause that much.
okay.
So this
Okay.
was a
Got it.
slowed down version of the animation.
Yes.
Okay, so Copernicus had this conviction. So what happened then? Well, he published this book. Unfortunately, he delayed publishing it for, a few decades. People knew about his views, that he believed in this heliocentric model, but and many of his friends urged him to publish this book, but he delayed publishing it. Finally, when it was published, it was basically a few days after he died. So it was published in 1543. He had had a stroke in 1542. We don't know if he was, conscious enough to be even aware that his dear work was actually finally published. But one of the reasons why, or one of the main reasons why he did not publish it is because there were a number of objections that could be raised against his model, which he did not have answers to. And I'll go through some of those objections. The first counter argument would be that his model contradicts common experience. So people in those times, when they moved, right, whenever they underwent motion in a cart or even on a horse or whatever, it was never smooth, right? It was never smooth. So you could always feel yourself move because, if you're going in a cart or a horse, um, you can feel whatever you're sitting on bounce around. And plus, if you're not enclosed inside a carriage, you would feel the wind on your face. the faster you were going, the stronger the wind on your face that you would feel. And so to have the Earth rotate around its axis and to go around the sun once a year, that would be like, we're talking about thousands of miles per second, uh, for not just, 10 or 15 miles per hour or kilometers per hour, whatever they were used to that time. So how much more should we feel ourselves moving um, if Copernicus's model is true? But we don't feel the earth move at all. We feel ourselves at rest. And so it was very difficult for anybody to accept that um, the earth is actually spinning and going around the sun. It was absurd. And these are just some simple figures. Like I said, we don't feel the vibrations, we don't feel the wind on our face. We saw last time, or maybe 2 sessions ago, actually last time, how Eratosthenes computed the size of the earth. And so if we are rotating, then on the surface of the earth, if let's say we are on somewhere close to the equator, we would be going around a circle with this circumference in 24 hours. So that's already, you can see, more than 1,000 miles per hour. That's just because of rotation. We're not even talking about the annual motion around the sun, all right, which would actually be orders of magnitude more in speed if you accounted for that. All right. So where are those vibrations? Where's that wind which I should feel if I'm actually moving at 70,000 miles per hour as per what we today know to be the Earth's speed around the sun. Um, all right, so that's the argument, the first argument based on common sense. Here was another counter argument. Common observation tells us that if there is a stone lying in the garden, it stays at rest and it doesn't move until something pushes it. Right? You can explain this using Aristotle. In fact, Aristotle's physics also predicts this. Right? The stone is already as close to the center of the earth as it can get. Its path is obstructed by the ground. So it's just lying there. It's not going to move. And if it is pushed in some other direction, not towards the center of the earth, but is in some other direction, violent motion, right? Then as soon as you stop pushing it, it will stop, right? Or very quickly. It might continue for a few seconds, but it will stop soon. The same applies to the earth, right? If the earth is going around the sun, why should this entire landmass made of earth and water move on its own? Like, who is pushing it? Who is keeping it in motion? There has to be something that keeps the earth in motion. There has to be someone who pushes the earth. That's how solids behave. We see that, and so it also applies to the entire earth. This is a more subtle argument. Suppose you're holding a ball and you're moving left to right on a skateboard. Okay, you throw the ball vertically up. So while you're on the skateboard, you push the ball vertically up, you launch it vertically up. Where would the ball land? Right? Would it land at the same spot where you threw it vertically up? That means, would it just come back directly into your hand? Um, or would it land at the same spot where you threw it vertically up? So whatever position the skateboard was in when you threw the ball up, maybe it just goes vertically up and comes back to that point. So you would have moved much forward by that time. Or maybe somewhere in between these two extreme points, right? The position where the ball was launched up and the position where you are, right, at the moment when the ball comes back to the ground, maybe somewhere in between. So most people in that time would have said somewhere, either at the same spot where you threw it vertically up, or somewhere, at least somewhere behind you, right? And that's also common sense. We feel that when you throw a ball up, when we feel the wind on our face, right, the ball is also going to experience wind hitting its surface. And so it's going to lag a little behind, right? Now, substitute the skateboard by moving Earth, okay, or extend the same argument to moving Earth. The same argument holds. If the entire Earth was moving, then standing on the surface of the Earth is equivalent to standing on a skateboard that's moving much faster. So if we throw a ball vertically up, it should land somewhere behind us, right? Somewhere. So if the Earth is moving in that direction, the ball should, land somewhere in the opposite direction. But it lands in our hands, exactly. So that means the Earth cannot be moving. Because common experience shows that when you throw something up and you're moving, it's not going to fall exactly back in your hand, it's going to fall somewhere behind. So, this is another way to look at it. These are all common sense arguments. Copernicus had no answer to them. This is an astronomical argument based on something called stellar parallax. So the argument is something like this. In a spherical Earth model, you have, in a spherical Earth geocentric model, the important feature is geocentric. You have a bunch of stars on a celestial sphere that's moving, that's rotating, but the stars are at the same distance from the Earth, right? Or almost the same distance, because the Earth is almost at the center of the universe. So if you look at any two stars, you will find the separation between them to be the same, irrespective of whether you look at them on a summer night or in the winter night, right? Across the year, the separation between the two stars should be the same, because you're at the center of this spherical universe. But if the sun is at the center now, and or almost at the center, you still have the starry sphere. Actually, let me put two specific stars here. Okay, I put two specific stars on the left side here. And now I have an orbit for the Earth. Okay, so let's say this is the Earth. And from the location where I've drawn it, if I'm looking at these two stars, they appear to have a certain separation. But a few months later, when the Earth is here, and I look at them again, because I'm much closer to them, I should see the separation between them to have increased, right? Because I mean, think about this angle, right? This angle, which is a relatively small angle when the Earth is in its initial location, and then uh, a few months later, you find the angle to have become this. It's actually bigger, right? So when you look at these two stars, they should make a larger angle. Um, they should subtend a larger angle uh, on your eyes. So this is called stellar parallax. Stellar parallax refers to how the separation between stars should change across the year if the Earth is actually moving around the sun. This is expected in a heliocentric model. Not expected in a geocentric model. And observations show that there is no There is no stellar parallax seen with naked eyes. So this seems to support the geocentric model over the heliocentric model. Now, one can still defend the heliocentric model and say that, well, what if the starry sphere is huge, really huge, and the distance uh, between the Earth and the stars from here and from here is almost the same, because the orbit of the Earth around the Sun has a size that's kind of insignificant compared to the size of the starry sphere, the diameter of the starry sphere. Then you would not notice any stellar parallax. But that seems more like an escapist. That seemed like an escapist argument for uh, people who supported the geocentric model. They said, your model should have stellar parallax. It doesn't have it, so you're just trying to escape by saying that the universe is much bigger, so that there is no stellar parallax. I mean, what's the point of having such a large universe? Why would God create a universe in which the stars are so far away from the planets and the sun and the earth? There's so much of empty space in between. What's the point of all that empty space? Just didn't make any sense. All right, so that's in short the argument from stellar parallax. And of course, last but not the least, there were religious arguments, religious objections, because there were several passages in the Bible which literally read seem to support the idea that the earth is stationary and the sun is moving. One particular passage from the Old Testament or Hebrew Bible um, had, describes a miraculous event where the Israelites, led by Joshua, are attacking an enemy um, an enemy town, and they need time. So they are winning the battle, but they need time to destroy the enemies. Okay, so what happens in that episode is that Joshua prays to God to not let the sun set, so that they get more time to fight and to completely annihilate uh, the enemies before sunset. All right, so that's this well-known passage, which, as you're going to see, is also going to have importance in when we come to Galileo. So when he prays for the sun to stand still, the sun stood still. So that means it was moving, and it just becomes fixed in the sky. The moon becomes still also. So there is light. There's enough light giving the Israelites time to destroy their enemies. And so every uh, church father who had commented on this passage had taken this literally, right? That the sun is moving, and the sun was asked to stand still. The sun stood still. And so this shows that the sun is what moves, not the earth. Like Joshua is not asking the earth to stand still. Um, the assumption is that the sun is moving and the earth is stationary. So if Copernicus were to be believed, then one has to, give up one's faith in the Bible. And, the Bible is the source of, was the source of meaning. Like all your entire worldview was shaped by it. So you would have to, it would completely uproot the foundations of your worldview to give up faith in it. And so um, when all of these arguments were taken in combination, there was very little reason that anybody had to believe in Copernicus's model, right? So even to avoid heresy, it was important that, and even if the model was simpler, even if the calculations became easier if you use that model, the uh, uh, the problem was not in accepting the model for making your calculations easy, right? In fact, many people adopted Copernicus's model to make the calculations easier for predicting where the planets would be, which positions in the sky the planets would be in the future. Remember, those astrological calculations were very important for Ptolemy's model. Um, and so if Copernicus's model eased the calculations because it was simpler, it had fewer parameters, then you could definitely use it. You could assume the truth of it for the purpose of calculations without believing that it is literally true, right? So it was okay to accept Copernicus's model uh, as an assumption for making calculations, but it was not acceptable to think of it as literally true. And in fact, nobody really took Copernicus's model seriously because uh, of all these reasons, right? And like I said, there was nothing, no clinching argument it had over Ptolemy's model apart from the simplicity argument, right? So, in fact, his accuracy uh, was actually no better than Ptolemy's. In some ways, it was actually a little worse than Ptolemy's. The calculations were easier, but the predictions were not were less accurate. So if you have two models that both explain uh, and both can predict what happens in the night sky, it's safer to rely on the model which is more aligned with common sense and supported by the Bible or supported by the religious texts that make up your worldview. So Copernicus was
Sir,
aware of all these arguments, and yeah, I'll just come to you. Let me just finish this particular slide. So Copernicus actually says that the scorn which I had to fear on account of the newness and absurdity of my opinion almost drove me to abandon a work already undertaken. So he took a long time to write up his book, and finally, like I said, when it was published, he had already passed away. And in fact, the person who got it published, whose name was Osiander, that guy was, you know, not he accepted a geocentric worldview. He did not favor his Copernicus's heliocentric model. So he added a preface at the very beginning of the book saying that this is just a model, right? This is just something to accept provisionally to make your calculations easy. It doesn't mean it's true, right? He wrote this preface and he didn't add his own name at the end. So the reader felt that this preface was written by Copernicus himself. So in a sense, the preface undermined what was to come later in the main body of the book. Yeah. So, question?
so it's not a question. I actually wanted to mention that your argument 5, religious objections, it reminds me of a blog post that I read about ancient science. And that was that like in his book on the revolutions, where Copernicus mentions all his theories. One of the reasons why he was also very apprehensive to tell the public about all of this was because um, he had originally dedicated this work to the Pope at that time, like the Pope of the Church at that time, and in a sense, like in a way, his arguments were not really very mainstream at that time, and so the church was unwilling to actually accept things that were dedicated to them, which they did not really agree with. And so, with that is also one of the reasons why Copernicus was very apprehensive to release his work.
Yeah,
This was
he was anticipating a lot of criticism, but at the same time, his work was not influential, right? Today we consider it very influential, but in his time, for the next 50 years or so, hardly anybody took his work seriously. The the way in which his work got used was to make calculations easier. So people took his model and they came up with new astronomical tables, which sort of treated this as an axiom, and then it's like let x be equal to something, and then you do your calculations, get your
yeah,
predictions. That doesn't mean that x is actually that value, right? So
yes, yes, and
you
it's just
just
absurd. It's very
mm,
absurd.
yeah, but Copernicus himself believed that the his model was true, so he was not
That,
postulating that model as just a calculational convenience. He was he actually believed that it's true, and the reason why the calculations became simpler is because it was true, right? Because it was more elegant, simple, and closer to how he thought the universe worked.
right.
So, all right, so that's about Copernicus. Um, but keep in mind all these arguments, because these are the arguments that have to be dealt with by anybody who is supporting the heliocentric model. All right, so 50 years after Copernicus, there were very few people, maybe 10 to 20 people, who literally accepted the truth of his model. And his book was also not influential. Very few people were taking his book seriously. I mean, there was some criticism, but nobody was really perceiving him as a threat. Like it's like, you start a YouTube channel and like you have very few views. Nobody really, even if what you're proposing is revolutionary and profound, the world doesn't perceive it as revolutionary. So that's how it was when Galileo came on the scene. 50 years later, 50 years after Copernicus. And when um, um, Galileo himself was quite influenced by Pythagoras and Plato early in his life. His father was actually uh, a musician, and you might remember that music and number theory were kind of blended by the Pythagoreans. So when stringed instruments used to be manufactured, they would be manufactured in a way that the lengths of the strings were in simple, like the tuning of the instruments was done, keeping in mind that when you have string lengths that are in a very simple ratio, plucking them produces a sound that is harmonious. Um, there were views like that by the Pythagoreans. But Galileo's father actually realized, when he did a lot of empirical experiments with different, tuning options, that the Pythagoreans were not completely correct. Right? It's not like you have to have exactly uh, the same, simple numerical ratios as people had believed for hundreds, if not 1,000 years. So Galileo sort of looked at his father and he sort of absorbed this view that, well, you can challenge authority, right? If you find from your own observations, experiments, and reasoning that something that has been accepted for a long time is not correct, it's okay to you know overthrow it. And after all, in spite of all the um, um, religiosity and faith in the church, there were epidemics happening, right? Common people's lives were generally not, happy. And so there was a lot of feeling of, what are we doing wrong? And sort of trying to look for answers beyond what the church authorities were giving them. So, Galileo was born in modern day Italy in the city of Pisa, and he was sent to the university to study medicine. But kind of similar to Copernicus, Copernicus at least studied medicine, right? He completed his studies, um, even though he dabbled in astronomy. But Galileo preferred mathematics. Now, he was quite intelligent, but he would he was also, you can say, arrogant to some degree. Uh, when he would argue, when he would argue with people who didn't know as much as he did, he would often insult them, be very sarcastic, and so and he would love getting into arguments with different people. So he had this nickname, the Wrangler, and he was unpopular among uh, you know a lot of people because of this tendency. One of the things that he observed, during his time in Pisa, actually he graduated from Pisa and then he became a sort of a lecturer there, a professor there. And during his time there, when he would go to the church, he would see these chandeliers uh, sort of oscillating, right, like a pendulum. And he would notice that whether the oscillations were more intense or less intense, right, whether the angle made with the vertical was bigger or smaller, the time period of oscillations seemed to always be the same. So he would notice things like that and get curious about why that is the case. So notice that he was looking out for these numbers again, right? He was trying to look at things in a more quantitative, mathematical way rather than in a very qualitative way. So um, he became influenced by Copernicus's model and he got convinced that it's true. Now, there's a legendary story, we don't know if it's actually true, but one of the things that Aristotle's um, physics says, and remember that Aristotle's physics and Ptolemy's astronomy are they both go together. Aristotle's physics is what supports Ptolemy's astronomy. So if you had to challenge Ptolemy's astronomy, if you had to support Copernicus, you obviously had to uh, challenge Aristotle's physics, right? You remember this argument. This is based on Aristotle's physics that, there's no reason why the Earth should start moving on its own or even continue moving on its own. Only ether, things made of ether, undergo circular motion naturally. And now suddenly you have something made of ether at the center of the universe and something made of earth and water going around it. I mean, it just doesn't add up. So Galileo actually tried to come up, or at least take the first steps towards building a new physics, because he knew that the new astronomy of Copernicus, the new heliocentric astronomy, had had to be supported over Ptolemy, not just based on astronomical observations, but also based on a new physics. So the old physics of Aristotle, for example, said that things that have more earth in them will fall faster than things with less earth in them. So if you take two balls that are of different sizes and very different masses, this being much heavier than that, Aristotle's physics predicted that the heavier ball would fall faster, and so there would be a drastic difference in the landing times if both of these rocks were dropped simultaneously from the top of a tall building. And so there is this legendary story that Galileo uh, uh, climbed the Tower of Pisa and he dropped these two balls. And at the bottom, people saw that the two balls landed at almost the same time. right? The heavier ball actually did land a little faster, a little sooner, but it was there was a very small time difference between them, which was contrary to what the Aristotelians had said, that they would land at very different times. Now, the main reason why, the main argument, the clinching argument that Galileo felt he had in defense of Copernicanism was that tides, when sea levels rise and fall every day, he felt that tides occur because the earth is moving. If the earth was stationary, there is no reason why tides should occur. So just like if you go into your bathroom and you fill a bucket of water or a tub with water, it'll just stay there. There's no reason why the water level will fluctuate. But if you take the tub or bucket and you start moving it around, say in a circle, then you'll find that the water level will rise and fall uh, at different places. Okay, it's very qualitative argument, but that's kind of what Galileo felt, that the tides are the best evidence that the earth is actually moving. Um, Today, of course, we know that's not a correct argument, but that's what he felt was his best argument. So even though um, he was right about the Copernican model being a better model, you can be right in what you believe without having the right reasons for believing the truth, right? So obviously, philosophers don't just want to believe the right things, but they also want to believe the right things for the right reasons. And of course, Galileo was trying to do that as well. But in retrospect, we know that his argument was using tides was not correct. But he tried whatever he could um, to gather evidence supporting Copernicanism. So one of the things he did is he heard that somebody in one of the northern European regions had built a spyglass, right, um, for looking at things closer, right, kind of like binoculars or telescopes, you can say. So Galileo built his own improved version of the spyglass, and initially he did it because he thought he could sell it uh, to the government. So he moved to Venice, where um, which was actually less under the which was not under the control of the Catholic Church that time, and um there was a navy there, and Galileo built this improved version of the telescope so that you could look out for enemy ships and see them sooner than you could with your naked eyes. And that's how he sold, like he got a grant for, uh, you know, mm, handcrafting many of these. But what he did personally with it is, this is actually, I think, from one of the documentaries. There's a nice documentary called Galileo's Battle for the Heavens. This is a still from that. It talks about his relationship with one of his daughters, which is a very moving account. But here his daughter's looking out at him uh, as in the, as he takes this telescope and turns it towards the sky and the things that you can see in the sky. So the first thing he did is he pointed it at the moon, and he noticed that the moon's surface was actually full of mountains and valleys, right? It was very irregular, and you could see shadows as if there were mountains on the moon, right? The line between the illuminated part and the dark part was not really a line. It was very irregular, as if, the surface has different elevations, blocking light somewhere, letting light through at other places. And so this seemed to contradict the view that the moon is made of a perfect substance called ether, because it seemed like it was just made of earth, like the way light behaves on, when it hits mountains on earth. That seemed to be what he was saying. When he turned his attention to the Milky Way, he saw that what was thought to be a continuous fluid in the sky at that time resolved into thousands, tens of thousands of stars that were not visible with the naked eye, but only through the telescope. So he saw that there were actually a huge number of discrete stars making up the Milky Way. Um, and rather than just a continuous fluid. So the Greeks had thought that this was really milk, Hera's milk that was sprayed in the heavens. There's a mythological story behind it. I think I've discussed that in there's one of the YouTube videos that you will find by me online is on a class I took for younger kids where I talked about this whole mythology behind the Milky Way. Anyway, this is not that important for the Copernican model. This is quite important. When he looked at Jupiter, he saw that there seemed to be four small planets very close to Jupiter. And again, planets because they also seem to wander relative to the stars. And not just that, but when he observed them night after night and recorded all this data, he saw that they actually seem to be moving around Jupiter. So in Ptolemy's model, everything went around the Earth. But now with his telescope, Galileo was seeing that there are actually new planets. Well, today we would call them moons of Jupiter, but you know, from the term vocabulary of that time, these would be sort of new small planets that couldn't be seen with the naked eyes, but could be seen with a telescope that seem to go around Jupiter. So you didn't necessarily have to have everything going around the Earth, right? If things could go around Jupiter, why couldn't things go around the sun, right? So that possibility was opened by these observations. When he turned the telescope to the stars, he saw that the stars did not become bigger. Right? Unlike the planets, which when viewed through the telescope become enlarged, become magnified, same with the sun and the moon. The stars appear to be points of light with the naked eyes and even through the telescope. So his conclusion was that the stars are actually quite far, as Copernicus had um, claimed. No, it was not just a possibility, but the fact that they didn't get magnified through the telescope meant that they were very far, and so the argument that there should be a stellar parallax in a heliocentric model was not necessarily a strong argument, because if the stars are really far, then you're not going to see a stellar parallax even if the Earth is going around the sun. One of the very few people who um, accepted Galileo's observations with the telescope readily was Kepler. Many people were actually skeptical of this new instrument. They felt that what Galileo was seeing was not necessarily something that was out there. It could be something that is produced by the instrument itself. Maybe the instrument itself is creating these false images that is making him think that there's something new out there. But Kepler wrote to Galileo that, because Kepler had independently, uh, uh, bought into the Copernican model. Uh, so the two communicated through a few letters. And Galileo said, "You're the first and almost the only person who, after a cursory investigation, has given entire credit to my statements. What do you say of the leading philosophers here to whom I've offered 1,000 times to show my studies, but who have never consented to look at the planets or moon uh, through the telescope, right? Because they were skeptical of this newfangled device." Now, here's a very strong argument or a very strong observation that Galileo made, which further lended support to the Copernican model. So in Ptolemy's model, you have the Earth at the center. You have the sun, right, going around the Earth, and you have Venus. So Venus is somewhere here, and it goes around the Earth as well. Okay, so Venus was actually put closer to the Earth than the sun for a variety of reasons. One of them, for example, was that it appears to be much brighter um, uh, and a little bigger um, at some times than other times. So if it was farther than the sun, then its brightness shouldn't increase as much, is was one of the arguments. So anyway, Venus was thought to be going around the Earth as well. And a very common observation that people had made since ancient times was that Venus and Mercury, both of them, stay close to the sun. So as the sun goes around the Earth, even as it moves relative to the starry sphere, Venus and Mercury seem to be tagging along with it, very close to it, like, like a child who's holding the hand of of his or her parent, and always going wherever the parent goes. And so in Ptolemy's model, you actually had the center of Venus's epicycle um, uh, lying on the same line as the Earth, as the line from the Earth to the Sun. So this would be the center of Venus's epicycle, and it might go like this. Uh, so when it was at the left extreme, it would appear just to the left of the Sun. When it is at the right extreme, it might appear just to the right of the Sun, but it always was hanging around the Sun. So when you want to see Venus, it has to be just before sunrise or just after sunset. So sometimes it's known as the morning star for that reason, or the evening star for the same reason. So this was Ptolemy's model. Now, what should be true if Venus was actually going around the Earth like this? If you looked at Venus through the telescope, you would expect the light from the sun to fall mostly behind Venus. All right, so you would expect to see a crescent shaped illumination for Venus. So you would expect Venus to be in the crescent phase, if you want to use that word, similar to the moon. But what if you had the sun at the center and you had Venus going around the sun and the Earth going around the sun as well? So let's say this is the Earth. When Venus is here, in front of the sun, uh, we would expect the phase to be crescent. But what if we see Venus when it is behind the sun, right, relative to the Earth? We're looking at Venus, and this time the sun is in front of Venus. Then you would expect Venus to be full, just like we see with the moon. As Venus changes its relative position with respect to the sun, as seen by us, it should go through different phases. When Galileo looked at Venus, he actually saw it goes through all phases. And so this contradicts Ptolemy's model, because in Ptolemy's model, Venus should only appear to be um, in the crescent phase. And so this is an observation which clearly supports Copernicus's model and which refutes Ptolemy's model. Right? Other observations can be explained by both models, like stellar parallax or the absence of stellar parallax. You can explain Jupiter having 4 planets going around it. Yeah, I mean, it's not there in Ptolemy's model, but okay, we could add it to Ptolemy's model and, you know, we could still have, a tweaked model that would work. Same thing with Milky Way. The moon's surface is full of mountains and valleys. So it's not really a problem for Ptolemy's model, but it is a problem for Aristotle's physics. So something made of ether, how is it that it seems to be visible, like as if it's made up of the same stuff that's found here on Earth? Uh, and then Galileo also looked at the sun through his telescope, not directly through the eyes, but sort of making an image, uh, casting an image on a screen behind. And what he saw is that the sun has spots. So if it's made of ether, why should something made of ether, which should be something perfect, have these blotches on its surface? Not just that, these blotches were born because he saw some of them come into existence when they didn't exist the previous day, right? So it's not like they moved from here to here. Uh, let's say you see this today, and then tomorrow this spot moves a little bit here, all of these move a little bit there, and then you see a new spot coming up. That means these sunspots are born and die. You can have sunspots disappear as well. So how is it that um, and these, according to Galileo, were on the surface of the sun? It's not like these were clouds hovering above the sun's surface, because when you saw them move out, right, move behind, out of sight here, you didn't see them um above the surface of the sun here, right? They just disappeared as if they are on the surface of the sun. So it looks like the surface of the sun has changes happening in it. So the sun's surface undergoes changes. And remember, one of the views um, in the worldview, in the Aristotelian worldview, was that there are no changes that happen in the celestial world, because everything there is perfect, made of ether, undergoes circular motion. Nothing gets created, nothing gets destroyed there. Things are eternal. Well, here you have changes happening there. How do you, like, obviously the Aristotelian worldview couldn't uh, explain this. So these were some of the famous astronomical observations by Galileo, which raised objections to the Aristotelian worldview, which seemed to refute the Ptolemy's model, at least this particular observation, um, the phases of Venus. And there were like small holes here and there which it poked, like the moon appears to be made of rocks and not ether. Um, the Aristotelian claim that heavier things fall faster seemed to be incorrect. But just poking holes is one thing, but having an alternative worldview, having an alternative astronomy backed by a new physics is what was needed. And the work for that was started by Galileo, although it would take uh, time. We would have to wait till Newton for a new physics to be built to support the Copernican astronomy. So Galileo had to do whatever he could. We'll look at some of his contributions to mechanics also. But I just want to mention here the controversy that he got into because of his support of Copernicanism. So all of these observations just reinforced Galileo's belief that Copernicus's model was literally true, right? That there was something seriously wrong with the Aristotle Ptolemy worldview, Aristotelian Ptolemaic worldview. Now, these moons of Jupiter that Galileo found, he dedicated them to, uh, the brother. So Galileo lived in Florence, and Florence was ruled by the Grand Duke, and he named the four moons um, after his four sons. So that obviously pleased the Grand Duke, and he got employed as the chief astronomer in the court. And so one day, so he kind of became close to the Grand Duke and to the royalty there. So one day, uh, one of Galileo's students was having lunch with the mother of the Grand Duke, breakfast with the mother of the Grand Duke, and she mentioned that I have heard that Galileo supports Copernicanism, that he thinks Copernicus's model is literally true. Doesn't it contradict the Joshua passage? She raised that religious objection out of curiosity. Like, I'm curious to know how Galileo defends Copernicanism, given that we have the Joshua passage, which seems to indicate the sun moves. So his student then assured her that Galileo uh, didn't really think the Bible's wrong or anything like that. Uh, and he wrote to Galileo after the breakfast. Now Galileo wrote back a letter to him saying that it seems to me very prudent of her to propose and of you to concede and agree that the Holy Scripture can never lie or err, and that its declarations are absolutely and inviolably true. So even though the Bible cannot be wrong, but its interpreters and expositors can be wrong. This was the position that Galileo was taking, that the Bible's true, but if a passage from the Bible appears to contradict what we know through astronomy, through natural philosophy, then we have to find some other way of interpreting it. We cannot go by the literal interpretations of the church fathers, because if those are, if your experience and logic is leading to a conclusion that goes against them, then you just have to reinterpret the Bible. Not just that, Galileo proposed an alternate interpretation. So what he proposed was actually interesting. He seemed to have been influenced by Kepler, who thought that, you know, so one curious feature of the heliocentric model is that you have the sun at the center and you have all the planets going around the sun pretty much in the same direction. Okay, so why is it that all the planets seem to be going around the sun in the same direction, and what's actually causing them to go around the sun? That question is not answered. If they are not made of ether, as observations of the moon, as observations of sunspots seem to indicate, um, then what makes them go around? Right? That's not how Earth behaves, according to Aristotle's physics. So Kepler seemed to have this view that there was something mysterious about the sun, that the sun sort of sent out invisible, well, I don't want to use the word forces, but something invisible. Like, people were aware of magnets that time, right? A magnet can exert its influence on something that is far away, right, at some distance from it. So in a similar way, maybe the sun is actually going around. Maybe the sun is actually what's powering the planets to go around consistently in the same direction. And what Galileo found is that the direction of rotation of the sun, as seen from the sunspots, was also the direction in which the planets were going around the sun. So maybe, maybe what's happening is, as the sun rotates, it is exerting some kind of magnetic influence on the planets and making the planets also move around in that same direction. All right, so that was the direction in which he was thinking. And what he proposed as an alternative interpretation of the Joshua passage is that when Joshua prayed to God to stop the sun, what he actually meant, and what God actually did, was to stop the rotation of the sun. Now, once the rotation of the sun stops, then whatever mechanism powers the motion of the planets around the sun, that mechanism also stops. And so all the planets get frozen in their path, and they stop moving. And so if we see the sun in the sky at that point, we're going to continue seeing it until this mechanism is restored or restarted. So, so Galileo actually wrote to the mother of the Grand Duke that, you asked my student this question. I agree, like he said, I agree that the Bible cannot be wrong, but the interpreters of the Bible are fallible, and the Joshua passage that you asked about can be explained in a way that's better than how these church fathers have explained. And here is my explanation. My explanation is that the rotation of the sun is what got stopped, which made the sun stand still in the sky. And that's what made the earth also stand still. So uh, that's how we need to interpret it. So this letter was shared by the mother of the Grand Duke with the other people. And uh, like I said, Galileo had many enemies, and people started complaining that his views were suspect ideas, right? This is not how the church fathers had interpreted the Joshua passage. He was actually contradicting them. Uh, and so um, between Copernicus's death and the time when Galileo was living, there was this event in the history of Christianity, this important event that happened, the Protestant Reformation, led by Martin Luther, where people started increasingly saying and believing that one can read the Bible on your own. One does not have to follow the interpretations of the church fathers, because the church was extracting a lot of money. And as an institution, as a religious institution, this happens with all religious institutions, that ultimately you have to run them as a business, and so you need to get some kind of regular source of money from the people, from your followers. And so if you paid a certain amount, you would be guaranteed a place in heaven. If you paid more, then maybe your relatives could also be guaranteed a spot in heaven. And there were things like that were going on. And so people were feeling, people of good faith were feeling that this is quite different from what we seem, what Jesus's life seemed to have been like. He was a very simple person, and the church is not really living according to those ideals. And so we should probably read the Bible on our own. Uh, and so the Protestants, these Christians were known as the Protestants, who sort of broke away from the church, and then they influenced local leaders, particularly in the northern regions of Europe, who were very happy to break away from the church, because the church was charging so much tax, and they had to pay a lot of wealth and donations to the church, and also follow the authority of the church. So many provinces uh, became Protestant, and this actually eventually led to a war, or the 30 Years' War, between the Catholic regions in Europe and the Protestant regions. And so in the church, there was a council that was set up after this Protestant Reformation, called the Council of Trent, which clarified the position of the church on various matters, and which set, um, you can say, rules for what could be done and what could not be done. And anybody who violated those rules could be punished. And so there was this organization called the Inquisition that was set up to examine the views of people who were that were deviating from the church fathers, and to punish them so that other people would not be influenced and misled by those suspect ideas. And so Galileo's views were also forwarded to the Inquisition. That letter was forwarded, that letter he wrote to the mother of the Duke was forwarded to the Inquisition saying that it had suspect ideas. The Inquisition examined it, and uh, they forwarded, so the people on the Inquisition panel, they felt like they're not very qualified to judge the status of Copernicanism, so they outsourced it to consultants who came back and said that, well, Copernicanism is actually heretical in theology and also foolish in philosophy. That means, the arguments based on sense experience, scientific arguments, as we would call them, against Copernicanism, those were also strong. Copernicanism seemed to violate the physics that we know, violated common sense, and also heretical in theology. So what the Inquisition decided to do then is they put Copernicus's book on something called the Index. So apart from the Inquisition, this Council of the Church, Council of Trent, they set up something called the Index, which controlled or censored what books got published, what ideas got published. And so they suspended the circulation of Copernicus's book because it had these heretical views until those views were corrected. So it was okay to use it as a mathematical model, assume its truth provisionally for calculations, but nothing more than that. So Copernicus himself had offered some reinterpretations of the scripture, and nobody really noticed him much because he lived before the Protestant, like his views uh, that he shared were shared before the Protestant Reformation, and so the, the church was not feeling threatened at that time. But in Galileo's time, the church was feeling very much threatened by the Protestant Reformation, and so they set up this index, and Copernicus's book was suspended until those controversial passages were corrected, specifically passages that seem to imply that uh, the heliocentric model was literally true. The Inquisition also asked one of the senior church authorities, Cardinal Bellarmino, to give Galileo a verbal warning to not continue to hold Copernicanism as literally true, right? Not to go about arguing with people and trying to defend it as literally true. And Galileo apparently agreed to it, to the verbal warning, because he probably knew what the consequences would be for violating it. Because there had been people who were literally burnt on the stake, like Giordano Bruno was one of them. He was not just burnt because of his belief in Copernicanism, but he had a lot of other heretical views, which in combination led him to being burnt, uh, condemned by the Inquisition, and punished by being burnt alive. So, uh, Bellarmino's position to Galileo was that it's okay for you to speak suppositionally about Copernicanism. That means accept it as a model to make your calculations convenient. Okay, that view is called instrumentalism. The view that scientific theories are just models for, making predictions that apparently work out. They are not literally true. So the view that scientific theories describe things the way they are is a view called realism. Today, most scientists are realists. In those days, most natural philosophers were instrumentalists. Copernicus, Kepler, Galileo, they were realists. Now, the church, so what Bellarmino said is, if you actually have good philosophical arguments, by philosophical he meant, defended by observations, experiments, reasoning, to irrefutably establish Copernicanism as true, then we will change our stand. Then the church can change its stand if it was demonstrated, if it was proved. But you don't actually have a proof. You're just going around saying that tides are the best proof for the Earth's motion. How do you know there aren't any other causes for tides, right? How do you know that God couldn't have some other mechanism for causing tides instead of having the Earth move? So he was not convinced by the arguments that Galileo was giving. Now, this argument that Venus shows all phases, uh, which can happen in a heliocentric model, but not in Ptolemy's model, this was also countered um, by people like Bellarmino by pointing out that there were other geocentric models, such as the one that Kepler's teacher had come up with. So Kepler's mentor was a Danish astronomer by the name of Tycho Brahe. So he believed in a geocentric worldview, and in his model, the Earth was at the center of the universe. The sun, so Venus and Mercury went around the sun, but the sun went around the Earth. So it was like a hybrid model. It was a hybrid model where you have, let me write that down, Tycho Brahe's geocentric variant. It was different from Ptolemy. You have Mercury and Venus go around the sun, which explains the phases of Venus, right? Mercury will be seen sometimes behind the sun, sometimes in front of the sun. But the combination, but the system, right? The system composed of the sun, Mercury, and Venus, but the combination goes around the Earth. Now, if you have this kind of model, if you tweak the geocentric model to make it have this feature, then the observations that Galileo had come up with, the full phases of Venus, they are also compatible with Tycho Brahe's model. They may not be compatible with Ptolemy's model, but they are compatible with other geocentric models that had Mercury and Venus going around the sun. And he had not really refuted that. So, um, so these were the counter arguments that the church had. And Bellarmino said that therefore you don't have a proof. And when you don't have a clinching proof, why are you insisting that Copernicanism is true? Right? I mean, there have been other people in the past who also put forth arguments defending Copernicanism, but they acknowledged that there's really it's impossible to rationally prove one of the models as true and the other one not. And so let's fall back on what our common sense and the Bible says. And if in the future somebody demonstrates with a proper proof that you, Galileo, don't have, but if somebody actually came up with a proper proof, then we would reinterpret the scriptures. Right? You don't go around offering your own reinterpretations, contradicting the church fathers. Some authority from the church will reinterpret the scriptures when that day comes. So he was kind of warning Galileo to stay away from offering his own interpretations. There was already a lot of that going on in Protestant regions, and it was a headache for the church to deal with, random people coming up with new interpretations every day. So, uh, so Galileo was let off with a verbal warning to not hold Copernicanism as true. Copernicus's book was temporarily suspended until corrections were done. The Pope, who was there at that time, Galileo met him as well, and he also assured Galileo that, well, okay, things are sorted out, don't worry. Uh, as long as I'm alive, nothing will happen to you. But turns out that Pope died, and a new Pope was elected. And Galileo initially thought that this is great news because the new Pope was actually a good friend of his. Uh, so Maffeo Barberini had actually composed a poem in honor of Galileo, um, and had supported him in many of his debates in when they were younger. And so he had become elected as Pope Urban VIII. So Galileo went and met him. He was very warmly received by his friend, and Galileo took permission from him to write about Copernicanism, to write about the Earth's motion, to write about the heliocentric model. And the Pope, as usual, just said that please, whatever book you want to write, you can write it, but please include one particular argument. And that argument is the following, that ultimately, no astronomical model can be proved correct. Whatever observations you can make of the night sky or anything you can make, there might be other causes behind it which we as humans can never understand, because God in his omnipotence can cause tides, can cause phases of Venus, can cause anything you see using mechanisms that are still unknown, which we may not be aware of. We just have one or two options in front of us with our limited minds. But God in his omnipotence could use any number of causes to make this, to have the same observations uh, um, be seen, right? So he said, please include this, but as long as you include this particular argument, you can write about uh, the heliocentric model and the arguments in favor of it and so on. Because this particular argument, which he asked to be included, it sort of says that, yeah, ultimately astronomy is inconclusive in uncovering the truth, because we never know how God acts. So Galileo was happy, and he went back to Florence, and he spent a few years writing a book defending Copernicanism, and it was written in the form of a dialogue. Again, see the influence from Plato. Plato wrote dialogues. So this was a dialogue. So the title was Dialogue of the Two Chief World Systems, right? A dialogue on the two chief world systems. What were the two chief world systems? Ptolemy's world system and Copernicus's world system. So it was meant to be a dialogue filled with debates between supporters of these two world systems. And so you had actually three people having a dialogue in his book. One of them was a supporter of the Ptolemaic system. The other guy was a supporter of the Copernican system. And the third guy was supposedly an impartial judge who was listening to the arguments on both sides and offering his impartial views. So the character who defends the Copernican system, his name was Salviati, and he was essentially verbalizing all the arguments that Galileo himself had. The guy who was defending Aristotle's physics and Ptolemy's cosmology, his name was Simplicio, uh, which in Italian referred to a simpleton, right? Like in Hindi, you might say Buddhu. Uh, so this guy was shown throughout the book as bumbling some unconvincing, arguments and not coming across as an intelligent, insightful person. The impartial judge, whose name was Sagredo, as you might expect, he typically favored Salviati, right? He would ask questions of both and invariably end up siding with Salviati. Now, so he wrote this book, and Salviati is literally defending Copernicanism to be true. Now, the Pope had asked him to include this particular argument, which he does. He actually puts it in the mouth of this character Simplicio at the very end of the book, and the argument is something like this. So these are Galileo's words translated in English. I know that if asked whether God in his infinite power and wisdom could have conferred upon water the observed, fluctuation in sea levels and all, using some other means than moving its containing vessels. That is, instead of moving the earth, maybe God could have caused the sea levels to fluctuate using some other mechanism. Both of you would reply that he could have, and that he would have known how to do this in many ways which are unthinkable to our minds. Exactly the Pope's argument. From this, I therefore conclude that it would be excessive boldness for anyone to limit and restrict the divine power and wisdom to some particular fancy of his own. Okay, this is the final thing that Simplicio says after being shown throughout the book to have been a simpleton. And Salviati replies uh, to this statement very sarcastically. What a marvelous and truly angelic doctrine. So, naturally, when this book was published, uh, the Pope was furious because he felt insulted and deceived. And when complaints were sent to the Inquisition, he refused to do anything to help his friend. In fact, he wanted to teach his ex-friend a lesson. So Galileo was summoned to Rome, even though he was 68 or 69 years old. He was asked to travel, uh, and the Inquisition again raised this, they raised this legal case from many years ago. Did Galileo violate the warning that he had been given by Cardinal Bellarmino many years ago? Bellarmino had died by then. So, but you know, uh, Galileo had shown them a written certificate about that warning. Um in fact, what the Inquisition thought was that Galileo was forbidden to discuss Copernicanism at all, right, in any way. Well, Galileo said that no, I had the permission of the Pope, and in fact, even Bellarmino said I could write about it as long as I did it suppositionally, as long as I didn't, you know, defend it as literally true. And in fact, I didn't. He says in this book, I wasn't really intending to defend heliocentrism, but I'm a guy who likes arguments, and I like playing the devil's advocate. And so I was just doing that. I was just playing around to make a weak argument look strong, right? So maybe I overstepped my boundaries, but I don't really think that Copernicanism is literally true. So obviously the Inquisition was not very convinced, because reading the book, and of course the Pope himself insisted that no, he needs to be put on trial, because uh, he also felt deceived that Galileo had not shared with him what had happened between him and Bellarmino in 1616. He came to know that, well, Bellarmino had already warned him not to hold Copernicanism as literally true. And Galileo, when he took permission to, publish this book, um, made no mention of the warning that Bellarmino had given. So uh, that context was deliberately hidden from him, and so he felt doubly insulted that this guy is just, you know, uh, he does accept Copernicanism. He does intend to, you know, uh, violate the beliefs of the church. So he must be put on trial. And so he was put on trial, uh, and Galileo continued to maintain that he doesn't literally accept Copernicanism as true. And so uh, when the sentence was given that his book be banned and he be imprisoned, uh, Galileo sort of agreed to abjure, right? That means uh, to give up his faith in Copernicanism publicly. So he sort of did that, and these are his words: with a sincere heart and unfeigned faith, I abjure, curse, and detest the above mentioned errors and heresies which the Inquisition recounted to him. during the trial. And I swear that in the future I will never again say or assert, orally or in writing, anything which might cause a similar suspicion about me. So this, prevented him from being burnt on the stake like Giordano Bruno and all, but he was still put under house arrest for life. So he was allowed to go back home to Florence, but uh, he was basically under house arrest. He could not leave his house without permission and without scrutiny on where he was going, who he was talking to, and so on. So he couldn't really, call friends or hold conversations freely with them. Uh, and there were friends who, later wrote to the church appealing on his behalf for a pardon, but nothing came out of that. So here's one example. One of his friends wrote a letter to the church saying, future centuries may find it strange that after he had retracted an opinion which had not yet been absolutely prohibited in public, so much rigor should be used against a pitiable old, 77, a person in his 70s, an old man in his 70s, who is being kept in a private, if not public, prison. He's not allowed to return to the city, the proper city of Florence. He was living on the outskirts. And his house uh, can't receive visits and comfort from friends. He has diseases that are inseparable from old age, require a lot of assistance. This shakes my heart, drove me to tears as I considered the vicissitudes of human affairs and the fact that he had so many uncommon honors and accomplishments whose memory will last for centuries. But, like I said, nothing came out of that. Um, in fact, there was a public uh, notice put that uh, the palace next to this spot, which belonged formerly to the Medici family, was a prison for Galileo, who was guilty of having seen the Earth move around the sun. So, under house arrest, Galileo was already in his 70s and he became blind. Um, and he laments in one of his works that, or his letters, this universe which I, with my astonishing observations and clear demonstrations, had enlarged 100, nay, 1,000-fold using the telescope, beyond the limits commonly seen by wise men of all centuries past, is now for me so diminished and reduced, it has shrunk to the meager confines of my body. Um, but one thing he did do, which I haven't mentioned here, is he spent the remaining years of his life uh, doing something non-controversial, right, for the church, relatively non-controversial. Obviously, it did hold significance for him, and that was mechanics, right? Not involving himself with the motions of the planets or what's going on in the night sky, but just examining how do things move on Earth. Experiments with inclined planes, pendulums, and so on, which you know, the 1D and 2D kinematics that you would study soon. That, all those things were developed by Galileo uh, in some detail during these years. And so he did publish another book uh, on mechanics. He died on Jan 8, 1642, was quietly buried in the church in a grave without any decoration or inscription because, he was being, after all, buried as a heretic. And so the Pope and the Inquisition let the Grand Duke know that it would not be proper to honor him in any way. In 1979, Pope John Paul II convened a commission to reinvestigate Galileo's case. And they wrote a report. The commission wrote a report uh, admitting errors on both sides. The church's side, uh, for example, the trial that happened, or the banning or the suspension of Copernicus's book. Those were errors they admitted, and also errors on Galileo's part, like defending the motion of the Earth based on the argument of tides, right? Why do tides happen? In fact, his original title for the book was On the Motion of Tides. It was not a dialogue on the two chief world systems. It was just on the tides. And the title was changed. I think the Pope himself gave that suggestion that you should change the title to a dialogue on the two chief world systems. So actually, the title ended up becoming a lot more grand. Otherwise, if the focus had just been on tides, it would not have made Galileo as influential as he became, because we actually know that his argument based on tides was not correct. Besides admitting errors committed, the report reaffirmed the ultimate compatibility of faith and reason, or science and religion, uh, which went together in the lives of many people, including Galileo. Like, he seems to have accepted the Bible uh, as true, but like we saw earlier, he felt that he had the right to reinterpret it according to what he was finding, and not simply accept the authority of the church or a literal interpretation that went against the natural philosophy that he was doing. And these are his words. Whatever the course of our lives, we should receive them as the highest gift from the hand of God. We should accept misfortune not only in thanks, but in infinite gratitude to Providence, which by such means detaches us from an excessive love for earthly things and elevates our minds to the celestial and divine. I'm giving this quote just to show you that um he was not an atheist. He was not somebody who uh, was trying to go against religion. He was religious from his own, from his own perspective. He was being religious, right? Even uh, throughout the trial, even if he did not accept the interpretations of the church fathers on those passages. Um, of course, later on, his burial was like he was given a proper burial once his influence grew, not during the time of the Pope, but later. Uh, so I think that's what I wanted to cover on Galileo's trial and his new astronomy. Like I said, the unfinished task right now is, how do you actually support Copernicanism uh, decisively? Uh, because all those objections are there. Um, I won't consider the religious objection, because uh, no religious text can be considered authority today. So, uh, I mean, people can still, based on what their faith is, but that doesn't count as a scientific argument. But the other arguments that we have are still to be addressed, which is that, uh, you know, lack of stellar parallax. I think that one is pretty clear, that the stars are actually very far away. So we won't get a stellar parallax even with the heliocentric model, but that seems more like a defensive argument. We don't have anything that, we don't have a new physics that can explain the astronomy. How is it that planets or entities made of rocks or made of earth and water can do circular motion around the sun? Why is it that when we drop things here on Earth, they don't fall towards the sun as they should in Aristotle's physics? They should fall towards the center of the universe. So they should actually fly towards the sun and not fall down on the Earth. So, so from scratch, we have to try to build a new physics that can explain uh, the astronomy behind Copernicus's model in a way that's also consistent with what we see happening on Earth. Um, and that's the experiments that Galileo did, which we'll talk about some other time when we are doing proper mechanics. All right, Kapil, should I take questions? Kapil, are you there? All right, anyone has questions? Otherwise, we can stop. All right, so we can stop here then. I'll log off. I'm not sure. Kapil, are you there? I think he's logged off too.
I'm here.
Okay. So should we just stop the session or anything you want to say?
I want to know, so where are we? We are almost every time students at the end of it, sir, when will we start doing our calculus and vectors and motion in a straight line and motion in a plane?
Yeah, so we can start that next because at least we have a need to build a new physics, we know. Uh, so 1D kinematics, specifically free fall motion, experiments on free fall motion were done by Galileo, and so we can start from 1D kinematics
And he
there.
was challenging the fact that Aristotle said that the speed of the body falling down is a function of mass.
Yeah, it's proportional to mass. Yeah.
Quite extraordinary. So he was the one who built the inclined plane and tried to disprove it. No, I'm wrong, I guess.
No, I mean, inclined planes were there since ancient times. I mean, you had ramps that obviously let you haul things in an easier way than, lifting it up vertically. It's easier
Yeah,
to drag along an inclined plane. But he used inclined planes to slow down free fall because
correct,
one of the questions is how exactly does free fall motion happen? Like when you drop something, it falls, but then at what speed does it fall? And does the speed increase with time? Does it increase with distance? Like how does it change? How does the speed itself change, if at all it changes?
yeah,
And it happens so fast that unless you slow it down, you can't measure these numbers quantitatively.
correct.
So one of the functions of the inclined plane was that this free fall would be slowed down in a way that you could track how an object, how the speed of an object changes as it falls, but it's falling at an angle, so the motion is kind of slowed down.
So we do not have precise clocks at that time that we can measure it precisely. So we need to slow down the motion.
Yeah, yeah. So the instruments were not so sensitive that you
Yeah,
could see it just happened so fast. Vertical free fall motion happens so fast that it's hard to get enough data, or it was hard to get enough data from it.
very cool. So we'll meet on Wednesday, 9 p.m. as we do every time, and let's start building new physics. Guys, are you excited about building new physics, or you're not able to figure out what physics we are trying to build, or what is really missing because of which we have to build new physics? Anyone there? Should we get everyone to join and have a quick 5-minute chat before we let
Yeah,
them
up to
go?
you. Up to you.
Okay, so how do I let them come in, Omkar? I have not used webinar format very often, so I'll make all of them panelists, right? Promote to panelist.
You can unmute all of them. Yeah, I mean, there are only 6 of them. You
Yeah.
can unmute them manually also.
Hello guys, Kajal, Akshada. There is someone called Perfectly I Am Perfect. I don't know her name, and Madhav. Arohi was also here, but I don't know. Okay. All right, guys. Can you switch on your video quickly and tell us what do you think where we are and where we are going? Are you able to understand it, or all of it is going above your heads?
हाँ सर, सब अच्छे से समझ आया। बाकी भी डॉट्स वी आर कनेक्टिंग हमें एक सही डायरेक्शन में लेके जाएगा, सो इट वाज गुड ओवरऑल।
तो क्या है, मुझे पर्सनली ऐसा लगता है दैट वंस वी अंडरस्टैंड द लॉजिक की, फॉर एग्जांपल एक्सेलरेशन ड्यू टू ग्रेविटी की जरूरत क्यों पड़ रही है, राइट? Why do we start finding those things which are missing? It starts making sense. I have personally a lot of people ask me कि कैलकुलस की जरूरत क्यों है. A lot of people do not आपके बहुत सारे टीचर जिनके साथ आप पढ़ते हैं उसका आंसर नहीं मिलेगा कि इंस्टेंटेनियस वेलोसिटी निकालने के लिए जरूरत है. अच्छी बात है, इंस्टेंटेनियस के लिए जरूरत है, पर न्यूटन को इंस्टेंट की जरूरत नहीं पड़ रही थी. मतलब देयर वाज सम अदर कंप्लीटली डिफरेंट रिक्वायरमेंट. उसका एक यूज केस ये हो सकता है कि कुछ इंस्टेंटेनियस मोमेंट पे कुछ चीजें चाहिए, उसके लिए उसकी जरूरत पड़ रही है. तो वी नीड टू अंडरस्टैंड एग्जैक्टली द लॉजिक ऑफ इट. और उसके बाद है ना, हमें ये जो फालतू की चिढ़ होती है ना देख के कि मतलब फिर से वही करना पड़ेगा, भगवान मेरा सिलेक्शन करा दे, कसम खाता हूँ उसके बाद फिजिक्स कभी छूंगा नहीं, वो सब नहीं होना चाहिए. इट
हाँ सर,
इज,
ट्रू, इट इज ट्रू।
है ना,
मतलब
इट इज वेरी
आज
ब्यूटिफुल.
हम जैसे एज अ स्टोरी वे में पढ़ रहे हैं, तो ऐसे कभी नहीं पढ़ा। लाइक अगर हम नॉर्मल देखें बाकी जगह जैसे ही पढ़ाते हैं, तो डायरेक्ट तुम्हें कंसेप्ट समझाया जो होता है, फॉर्मूला लिखा है कि हाँ ये जी है, 9.8 होती है वैल्यू, एक क्वेश्चन ऐसे सॉल्व करेंगे, हो गया। आज मतलब जैसे हम और भी साइंटिस्टों के बारे में जान रहे हैं, तो मतलब वो धीरे धीरे बिल्ड होगा। अभी तो मैं ही कहूँगा बेसिक है, बट इट इज गुड।
हाँ, तो उसमें चैलेंज ये भी है कि ऑडियंस जो है, स्टूडेंट्स हैं और पेरेंट्स हैं, वो भी यही चाहते हैं कि सर बस इंजेक्शन निकालो, बच्चे के बम में लगाओ और वो सीधा आईआईटी या नीट पहुंच जाए, है ना, पढ़ाना वढ़ाना हो जाएगा बाद में. तो इन सम वेज वी आर चैलेंजिंग दैट अजम्पशन एज वेल. यू कैन क्लियरली सी, क्योंकि अब 4 लोग रह गए यहाँ पे, तो दैट दैट ऑल्सो रिफ्लेक्ट्स द फैक्ट कि while it is a good way of studying, a lot of people do not have time. सब भाग रहे हैं मतलब, है ना. But that is fine. Hopefully we will make a dent in this. ओमकार का सीधा सा assumption है, when I discussed with him, if you are not liking physics now and if you end up in engineering or medicine, कितने टाइम तक झेलोगे वो चीज जो चीज आपको पसंद नहीं है, राइट? यू हैव टू फॉल इन लव विद साइंस और you are going to bolt out of it. A lot of people get into IIT and figure out in their first semester, I was one of them, that they don't want to be engineers. उसका रीजन यही है कि घोट घोट के पहुंच तो गए, सवाल लगा लगा के पहुंच तो गए आईआईटी, पर उसके बाद कब तक वो करते रहेंगे, राइट? नाउ इट बिकम्स अ डेली अफेयर आफ्टर दैट. सो द अटेम्प्ट हियर इज टू डेवलप understanding, true love in science, so that it is a long term endeavor. आपकी जिंदगी 18 साल में एग्जाम लिखने के बाद खत्म नहीं हो जाएगी, आपकी जिंदगी वहां से चालू हो रही है, राइट? एंड दैट इज, फॉर दैट it is important that if you're choosing a career, engineering or medicine in this case, there should be longevity in it. ये नहीं होना चाहिए अब engineering कर लिया चलो अब MBA कर लिया, क्यों करना MBA, मतलब ही नहीं है, राइट? So that is what it is, guys. So Madhav, Kajal, Akshara, and I think perfectly I am perfect is most probably Arohi Pandey. We will catch up again on.
No, sir. This is Himanshu.
This is Himanshi. Okay. So Madhav
Yeah,
said
sir, Himanshu.
Himanshu.
Sir,
Okay.
Himanshu.
Himanshu. So Himanshu, Akshada, Kajal, if you want to say something, say it. Otherwise, we'll take leave and we'll meet on Wednesday at 9 p.m. Wednesday meaning 21/3/24 July.
Yes, sir. We'll meet then.
All right. Akshada, Kajal, all good? All right, Omkar, thank you again so much. It
Sir?
is so late. Yes, Arohi, tell me.
Sir, just the previous doubt that I asked you on the Telegram, and Ori sir replied on it. Same. So you explained about equinoxes. So I want to ask that does the gravitation anyhow plays any role in equinoxes?
Omkar, you have to answer. I am not that well versed.
Yeah, no, gravitation has nothing to do with equinoxes because equinoxes can be explained using Ptolemy's model very well. In fact, uh, yeah, I think we have a model for um, that also in the game. Uh, I may not be able to open it immediately, but you can have a spherical Earth uh, at the center, and you can have the sun going around the Earth, and you can explain equinoxes quite well with that model. So equinoxes happen. Um, Let me see if I can open it. You just give me 1 minute. I'll have to depend on this guy again, assuming he has done the gameplay. Still sphere. Yeah, it's not. I can't immediately see a video on it. I'm sure it will be there in one of the walkthrough videos, but um, oh, here it is. Hold on. Hold on, I'm just trying to go to the appropriate point in the video. Uh, Let me just share my screen again. I hope you can see this model here.
Yes, sir.
So this is actually a 3D model of the celestial sphere. You can see the outer sphere, and you have a spherical Earth in the middle. And this lamp is actually representing the sun. Think of it as occupying its own like inner shell, right, in between the outer starry sphere and the Earth. And there is again a laser light that's actually directed from the sun towards the center of the universe. So it's going to pierce the Earth at some point. Let me see if this plays. Well, you can play around this with this model. I don't know if the person who made this video is going to do all the things. Uh, so one thing you can notice here is that um, the starry sphere we know rotates once every 24 hours, right? So when the sun is at this position, um, it's going to go around in a day, and this laser light is going to fall on this latitude line, all around this latitude line. And that's actually called the Tropic of Cancer, because back in 1000, 1500, 2000 years ago, whenever the sun was in that position, it would be in front of the constellation Cancer, the crab. It's called the Tropic of Cancer. Tropic means turning around. And what turns around is actually the sun here. So the sun's laser light is falling on this. After one day, the sun's laser light would fall slightly lower. After another day, it would fall slightly lower. After another day, it would fall slightly lower, and so on. After around 3 months, it would fall on the equator. And after 3 more months, it would fall on a latitude from which it will again turn around and start to rise up. So this is called the Tropic of Capricorn, um, which is again called by that name because the sun, when it reached there, used to be in front of the constellation Capricorn. Um, it's a little complicated, why today it's no longer in front of Capricorn. It's again because of this phenomenon called precession, which I roughly alluded to earlier. But when the Earth is spinning and going around the sun, it actually wobbles. It wobbles slowly. It's not just spinning and going around the Earth. Around the sun. That wobbling actually changes where the axis is pointing to. So it wobbles in like a rough circle. The axis goes around in a rough circle once every 26,000 years. And so what constellations it's pointing to, or what stars the North Celestial Pole is coinciding with, changes across 26,000 years. Because of which the constellations um, of the zodiac, uh, in front of which the sun is on a particular day of the year, that also changes. But don't worry about that. Um, the point is that this the 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 light of the sun is falling perpendicularly in this still image on the Tropic of Cancer. So if you are actually directly underneath that laser light, um, imagine yourself somewhere on that latitude. Across the day, the sun goes and its laser light hits everywhere on that, every place on that Tropic of Cancer. So if you are somewhere here at noontime for you, the sun will be directly overhead. That's what this laser light is. Any point that it's falling on is directly underneath it at noon. So, but notice that if you were somewhere here, right, somewhere, um, let's say further up here, you would see the sun pretty much the whole day, right? Because the sun would be visible to you since it's not directly over the equator, right? It's a little elevated. Because it's elevated, for people who are in the northern regions, the sun is actually visible in the sky for more than 12 hours. So if you imagine the sun was directly over the equator, then it would be visible to everyone for exactly 12 hours. Does that make sense? That if the sun was directly, over the equator, it's not, it's a little elevated. Let me see if.
Sir, I got it. One
Yeah.
stupid, very stupid question, but yet, uh, we know that the lines are imaginary. But couldn't we just do it without them? But at the end of the day, we know that the lines are imaginary. So why are we literally like imagining them and doing our work? Can't we
Which
just ignore
lines? Which lines?
latitudes and longitudes, imaginary lines? Couldn't we
Oh,
just
they
do
are
it without?
important. They are important because, uh, uh, practically also latitudes are very important because you can show using high school geometry, for example, that the elevation of the pole star, the angle at which you see the pole star, is exactly the latitude on which you are. So let's say you want to sail west, like Columbus, along the same latitude. then you have to keep your ship in such a direction so that the elevation of the pole star on your right side is exactly the same. If the pole star appears to rise further up, that means you have actually come closer to the North Pole. And if it goes further below the angle at which you started, that means you have gone further towards the equator. So staying on the same latitude can be done by looking at the stars as well, because their elevation can be figured out. I mean, their elevation maps directly to the latitude. Uh, uh, Secondly, when the sun is at the northern latitude, that's when you have the summer season in the northern hemisphere. Because for people living in the northern half, um, the sun is visible for longer than 12 hours. And actually, the longest day for them is when the sun is on the day of this they call it summer solstice, the day when the sun stops on the Tropic of Cancer and then it turns back. So likewise, the day when the sun's light falls directly on the equator, that's called the equinox. Nox means night, equinox means equal night. So same duration of night as day, that is 12 hours. And then on the uh, winter solstice, which is the day when the sun's rays fall directly on the Tropic of Capricorn, those living in the southern hemisphere will experience the longest day when the sun would be visible for more than 12 hours. And for how long the sun is visible again depends on the latitude. So the length of the day depends on the latitude, right? So the time between sunrise and sunset depends on the latitude, and you can work out the geometry. It's um, a little more complicated than high school geometry because we're talking about 3D here, but you can argue that there will be a point above which there will be a latitude above which the sun will be visible for 24 hours um, on the day of the summer solstice. So that latitude, we can prove it that will happen, and that latitude is called the Arctic Circle, above which you would see the sun never set completely. Um, Longitudes are not that important. Longitudes are imaginary, actually. Latitudes are not imaginary because if you have the spherical shape of the Earth, so there is an objective latitude that cuts the spherical Earth into two halves. And that's the equator. So it's not just an imaginary thing, whereas longitude is something which longitude you call as 0 degrees, that is completely a convention. But which latitude you call as equator, um, that is like there cannot be any disagreement about that because everyone on Earth would agree that this is the middle latitude. But everyone would disagree on where the 0 degree longitude is. Every country would want the prime meridian to go through it. So the powerful countries obviously get to, they control uh, what, where the prime meridian is.
Okay, so thank you so much, sir.
So is this the reason why summers, like the days in summers are long for us and in winters they're shorter because of the movement of sun and the planet?
Yeah. So actually, if you see here, in this sphere, you see the zodiac band is actually not horizontal. It's tilted at an angle. I don't know if you can make that out. Towards the left, it's
Yeah,
higher up.
yes.
Towards the right, it's coming down. So the sun is actually, uh, it's actually going up and coming down. In coming down in the winter, and right now it's at the summer. So here it's on the equinox. Here it's gone up again. Uh, but on a particular day, it's going to rotate around 24 hours, right? So it maintains the same latitude, but across different days, it actually goes down and comes up. So that angle of inclination of this band with the horizontal is around 23.5 degrees. And
Just
so
the
when
angle that
when
Earth is tilted.
yeah, and so that's why when the sun is 23.5 degrees above at its left extreme here, above the horizon, its rays are falling towards the center of the earth, and so it's going to hit at a latitude of 23.5 degrees north. And likewise here, 23.5 degrees south. So what is the latitude? It's basically the angle made by let's say a point on the latitude with the center, right? So as measured from the horizontal, as measured from the center of the earth. So this line would be 0 degrees at a 0 degrees angle. If I ask what is this latitude, it would be whatever this angle is. So the North Pole would be at a 90-degree latitude, 90-degree north. South Pole would be at a 90-degree south latitude. Tropic of Cancer is at 23.5 degrees latitude, because the path of the sun around the celestial sphere over a year, that path is called the ecliptic, that is inclined at an angle of 23.5 degrees with the celestial equator. If you imagine an equator on the surface of this starry sphere, that would be a celestial equator. It would also be horizontal and concentric with the Earth's equator. But the ecliptic of the sun, so the sun's latitude on the celestial sphere is actually changing over the year in this model. It changes from plus 23.5 to minus 23.5 degrees below the
But
celestial
sir,
equator.
the Earth is not straight. Like it. The Earth is also at an angle. It's we read in high school. Like,
Yeah,
it's
so
not straight. That
yeah, so in a heliocentric model, that's how you visualize it. In a geocentric model, you visualize the Earth straight, but you visualize the sun at an angle, at this angle of 23
oh,
and a half.
okay.
In a heliocentric model, uh, I think there is an animation of that. Let's see. In a heliocentric model, uh, you would have an orbital plane for the, yeah, this is the one for the sun and the Earth. So if you notice right now, the axis of the Earth is vertical. And the sun's rays are hitting on the equator. So if the Earth's axis was not tilted, the sun's rays would hit on the equator every single day of the year. And so as the Earth rotates, even as it goes around the sun, every point on the Earth would be illuminated for 12 hours. Um,
Right. Got
but
it.
now the axis gets tilted, and so with a tilted axis, as the Earth rotates, one thing you'll notice from this model is that the sun's rays are actually hitting the Earth at different latitudes as the Earth goes around. So right now it's at the equator. Oops. Yeah, now it's on the Tropic of Capricorn. Okay, this person, uh, he didn't really play around with it much, but uh, if I just go back for a second. Yeah, here, because it's tilted towards the sun, so the sun's rays might be hitting at a northern latitude here, around 23.5 at this extreme, and then on the other side, it would hit at a latitude of 23.5 degrees south. So in a heliocentric model, this is how we explain that, because we assume the orbit of the Earth around the sun is this horizontal plane, and so we tilt the Earth's axis. But in a geocentric model, the Earth is um, the Earth's axis is vertical, right? You see here, the Earth's axis is vertical. It's the sun that's actually going up and coming down
Right. Yes, sir. I
across
understand.
across the year. Across a day, it just goes around, right? There are two different motions. one motion is across a day, it just goes, hits every point at that latitude. But across different days, it slowly comes down along this ecliptic band.
Yeah, so
And
in an extension, when many days, that is a year, has passed, it has almost, taken a revolution of Earth.
yeah, one complete rotation around, revolution around this band, the zodiac band,
Yeah.
would make 1 year. And so the distance from, I mean, the duration between one summer solstice and the next summer solstice would be 1 year.
Right, yes, sir.
But there would be
Got
two equinoxes in a year, because once when the sun is going down,
And once when it's coming up,
one
yes.
yeah. So from when it's going up to down, that's the southward motion. And then when it starts going up, that's like the upward or northward motion, whatever you call it. So in India, we call it Uttarayana and Dakshinayana, the up northern path and the southern path.
Yes.
Sir, as you mentioned that the powerful countries decide whether the placement of prime meridian. So is that the reason that United Kingdoms are powerful? So that's why the prime meridian passes across them?
Yeah. So there is nothing special about the prime meridian. It is just, you know, a convention that it passes through
So
that particular place. Yeah.
can we really change its position in the upcoming years? Like if another country grabs more power, just
Yeah, I think France had that power at some point, but UK has it now. So, but it's ultimately a convention. So I guess once you have a consensus, then it becomes hard to change completely the consensus. But longitudes are not that important uh, from an astronomical perspective, because they don't really mean much, but latitudes do, as we just saw over the last several minutes. Because latitudes, when the sun is over a particular latitude, it is telling you which day of the year it is. Literally, it is telling you which day of the year it is. Because the sun is over the Tropic of Cancer on June 21st. You know it will be over the Tropic of Capricorn on December 21st.
December 21st.
You know that it will be over the equator twice on March 21st and September 21st. One of those days, might be plus minus one, but around that time. So you can actually make a sundial irrespective of which latitude you are in, because the sun's position over the celestial sphere changes. And so every day, because the sun's elevation here is changing on the celestial sphere, if you plant a vertical stick on the ground, the tip of the shadow, the tip of the stick, the shadow of the tip of the stick will make a slightly different trajectory every single day of the year. So you can actually track that over a year, carve out those trajectories, and after a year it's going to repeat. So you can have a local sundial that identifies the day of the year based on which trajectory the tip is falling on.
Oops.
Tomkar, should we end it here?
Sure.
All right, guys. Good. Anything else, or we meet again on Wednesday night?
We'll meet then, sir.
All right. Bye bye.
Okay.
Tomkar,
Thank you so much, sir.